Hello everyone, I'm Mr. Lambert from Cartesian Company located in France. Today I'm going to discuss about the constraint we meet when we design a loudspeaker, especially about the non-linearity for the motor structure, for the suspension, and also for the cone, the membrane, which is the topic a lot of discuss in the hi-fi world. Before that, a couple of words about my company. So, as I said, we are located in France. We are focused on quality and innovation. This is very important because there are so many loudspeaker drivers on the market. I personally believe the market is completely saturated by many references, very similar design, similar performances, that it's important for me to say we are focused on innovation. I mean, do something different, better, help to audio world progress. And we do only high quality products. We will never build a $15 speaker. That is not our job. And also, I don't believe it is a good way to work. So we integrate in the company all the jobs, from the engineering to the prototyping to the production. For the engineering, we use the best tools available: Clipel, Loadsoft, MATLAB, SolidWorks for the 3D, and so on. And we have all the measurement system we need to make top-of-the-art products. We have a small production line in France. I say small because it's a wish for us to keep it small. In that way, we don't have minimum of quantity larger than 50 or 100 pieces, which is very convenient to start a project for small company or people who want to do something new. It avoids to expense too much after the R&D investment. We can start with a small order, it's fine for us, and also it's much more faster for us to produce your driver. We can build roughly 200 pieces per week, so it's fast. Next, our main job is to build specific or exclusive loudspeaker. You can see in this show in Munich some drivers we did for high-end brands from a white page with a technical brief or the engineer from our customers, and we do everything for them. I will show some picture next. We also have a small products lineup. We did it small because I don't want a very large catalog of products with many similar products. At the end, the customer doesn't know which one is the best for him. So what we do is one 6-inch woofer, the best one, one 28 dome tweeter, the best one. If you want to change it according to your need, we will change this reference, but we won't let you decide among an endless list of products which one is the best. And so these products are distributed by two distributors, TLHP in France and Solen in Canada. One more time, we don't do as our competitors. I don't want to have many distributors everywhere in the world. I don't want to create a fight club between the distributors to know which one has the lowest price and so on. So we have one main distributor in France, and from him you can buy all our product range. This product range is, in fact, a platform to be used to modify the products and adapt it to your concept, to your ideas, to your project. So we can change everything with our drivers very easily, because in our R&D lab we have many spider stiffness, many voice call, many cones, and we can adapt the driver up to you. So just an example about exclusive driver we do. So this is a brand everybody know. It's an own brand in Munich. I can name it. It's Avant-Garde. Usually we don't name our customer, but they allow us to name them, so we do. We did everything for that woofers. The frame is injected aluminum frame. It's an exclusive design. We designed the frame according to the customer wish. I show you it again. You can see the frame. It's a very specific design to be attached on the enclosure directly. The motor structure uses a 4-inch voice coil able to handle 1000 watts according to the AES 2012 standard. And there is a linear excursion of more or less 10 millimeters with 80% of nominal value for BL and KMS. So this kind of driver is not available on the market. And if a high-end brand buys something on shelf, it lost its competitiveness because someone else can do the same, just buy the same driver on shelf and put it in an enclosure and it's done. For this kind of very high-end brands who try to do every year something better, they need exclusive drivers as we are able to provide. Next, I will just take one example of each market we work with. The first market is high-end product. So this is a product among our product lineup. By the way, I have this driver in my booth. If you want to take it on hands later, you can. And so in the high-end lineup, we use very high-quality material, titanium voice coil, small, short coil in a long gap to keep very large force factor. Also, this curve about the KMS is very interesting because we see the stiffness of the suspension is nearly constant. I will discuss it later, so it keeps the resonance frequency constant. You can see also the frequency response is nearly a wideband speaker, so it's really easy to use. The second driver I want to discuss to introduce our products lineup is a coaxial driver. It's developed for professional audio. The idea was to get a very good sounding coaxial speaker with a carbon fiber cone with a smooth cone breakup, keeping high sensitivity. And for this driver, we can provide the passive crossover if you want, so it won't be perfect for your design, but at least you have a base to continue your development. We have a great sensitivity, 93 decibel for 2.8 volt at 1 meter. And the compression driver can be easily replaced if you burn it during the lifetime of the product. The next product is for the market monitoring studio. So this is a tweeter, 32 millimeter diameter soft dome. This has all our speakers. This one has something special. You can see on the tweeter you have two peaks on the impedance curve. Usually a tweeter is a sealed back chamber, so you have only one peak. Here we have two peaks because we have an internal resonator which help to increase the sensitivity of the driver in the mid band and use the tweeter from 1.5 kilohertz, which is very convenient for monitoring system, keeping the nearly constant directivity out of axis. For this driver, we have a aluminum machined faceplate that you can add on the tweeter if you want to increase the sensitivity in the mid. And on this graph here, you can see that only with a 5.6 microfarad capacitor, you get the yellow curve, which is nearly perfect to use a woofer around 1.5 K. One more point about that tweeter is with the back chamber. I said we have inner back chamber. Most of the tweeter of the market nowadays, they have back chamber for the dome. But not so many have back chamber for the surround. And behind the surround, we have high sound pressure, which must be damped and managed. So this is what we did in that tweeter too. And that helped to get a cleaner mid-range. The last one is a small subwoofer, a 4-inch subwoofer we developed for high-quality multimedia products. So we have a very large linear excursion, roughly more or less 6.5 millimeters. And this subwoofer has a very wide frequency response, so you can develop a small two-way system as we did in that example below. This kit is available in our distributor website. It's a super cool kit to design for passionate people. Okay, this is to introduce the company and what we do. Now I'm going to enter into the topic of today about compromises in electrodynamic loudspeaker design. First, I'm going to discuss about the market needs against the possibility we have, and so the compromises we have to do. Next, I will discuss about the motor structure constraint, the moving part constraint, and the solution we want to offer to improve what is already existing. So market needs. I choose two pictures. One is a famous ALTI lancing speaker, one of the first in the world. Everybody knows that. Many people believe it's still something very cool, which is not wrong. My only concern with that product is it's a big one. If you live in a small apartment, you have to forget it for your living room. And so I believe our target is to offer all the emotion of the music in your home. I mean, with a system compatible with your way of life. So it must be compact and it must reproduce a real sound. The next one is a French one. It's a De Vialet system. It's a great system, a lot of engineering. It's compact, but I believe many people would say this is not high-end system, it's not so realistic sounding and so on. So what I want to say with these two pictures is nowadays the market needs is to get compact products for room integration. We need a very large dynamic range. The current electrodynamic loudspeakers are still not able to cover a 100 decibel dynamic range without any compression, or you need big drivers, 15-inch, because such a SPL needs cone excursion, and with regular motor structure design, you lost the force factor after 3-4 millimeters, so you kill the dynamic range. Low frequency extension. In the same way, you need a high excursion to make low frequency, and if you don't have completely linear motor structure and suspension design, you don't have low frequency extension. THD, IMD, let's say sound quality, I don't want to belong with that. THD, every note distortion, intermodulation distortion, for me it's much more relevant than THD. And fast transient response is the capability for the driver to accelerate and stop to play sound when we want he stop and play when we want he play. And this is maybe the most important point. So if we translate it into technical points, we want large linear excursion. We want low nonlinearity with BLX, force factor, KMX6, the suspension, LE, inductance. We want the resonance frequency stability. We want low inductance modulation. And we want a cone which is light, rigid, and damped. Most of the time we forgot that point. We can find many very rigid and light cone, but the damping is not good, so you have a big cone breakup and you cannot deal with. So, just a quick back to basic. We are still playing with a technology which has 1 century this year. Mr. Rice and Mr. Kellogg's, these guys, did the first electrodynamic loudspeaker 1 century ago. And we are still using the same technology. We still use the Laplace force, I mean voice coil moving in a gap. We put a current in the voice coil, we get a force, we attach a cone to the voice coil former, and we get a sound pressure. As basic as that. It's a very great idea, but there are some limitations. The first limitation is the force factor. If you take top lay 5mm 8. You design a T shape because you learn a bit about the asymmetry. You put the voice call at the right position in the gap to avoid the offset. You did that job, okay. At the end, you still have a link between the height of the voice coil, the height of the gap, and the linear excursion, the linear force factor you will get. If you want to enlarge the excursion capability, this is the force factor, and you see the voice coil in blue, you have to use a different voice coil. You have to increase the height of the voice coil. If you increase the height of the voice coil, you will increase the moving mass because you will add Cooper. And so you will kill the sensitivity of the driver. By the way, roughly on the moving part, the voice coil is roughly 50% of the total weight of the moving part. So it's not negligible. You will also increase the inductance of the voice coil. So the transient response, the impedance curve at the end of the frequency, all these parameters will be compromised by the inductance. You will increase the RE, so the resistance of the voice coil. You can choose a larger wire section to avoid that, but you will increase the weight again. Maybe you will have to do 2 layers with your voice coil, so it will be heavier. You have to enlarge the gap, so you will lose the magnetic field in the gap. So it's always the same constraint. With conventional motor structure, you have a link between the cone excursion, the linear excursion I mean, really linear excursion, and the weight of the voice coil, the inductance of the voice coil. And this is the kind of compromises we want to solve with the technology I will introduce just after. Good solution with electrodynamic speaker design is what we do with our high hand range is the underhung motor structure. You have a short coil in a long gap. So this is a great solution, but there is no axial magnet available on the market able to produce a magnetic field strong as 0.8 to 1 Tesla in a gap 8 of more than 20 millimeter 8. It means if I want to have a cone excursion, linear cone excursion, higher than 6 or 8 millimeter, I have to enlarge my gap. I lose my B and I go back to the same constraint as conventional design because I have to use 2, 3, 4 layers voice coil. So I increase again the moving mass, I increase the inductance, and so on and so on. So it's a good solution. It put the limit a little bit forward, but it's not a definitive solution. The next issue is about the suspension. And I really want to put it on the table because for me, I believe this topic is not enough addressed in the audio world. I know for pro audio, the spider stiffness is not constant, and they are happy with that because they use the stiffness as a protection to avoid the large excursion and damage on the speaker. But just think about it. When you have the stiffness of the suspension changing according to the position of the voice coil, it means you directly have the resonance frequency of your driver changing according to the position of the voice coil. You have the datasheet of your driver, it's noted, let's say 40 Hertz. Yes, for very small signal. If you are playing loud, it may be 65, 70 Hertz. If you read Voice Call magazine, you will see all the KAMS curve from Clement database. It looks like this typical example I show here on the right. You see the curve, the U-shaped curve. So you change the resonance frequency when the speaker is playing. So the enclosure you design is not good anymore. It's not the same output at low level and high level. And the dynamic of the music is huge, especially in low frequency. So if you have a bass player and you play it low or high level, it won't sound the same. Even if the musician is playing lower or higher, it won't sound the same. It's not realistic, so we have to solve that point. If we change the FS, we change the QMS, we change the TNS parameters. So this is a point to really consider into the loudspeaker design. The last one is the cone breakup. As I said, we can find easily on the market some rigid and light cone. But it's not so easy to find light, rigid, and damped to avoid the cone breakup at the end of the band. Now, consider the moving mass as sub-assembling, and you have a budget for the mass of this sub-assembling. If you already put 50% of the weight into the voice coil because you want to enlarge the BL curve, you don't have any more budget to add damping of your cone and avoid the cone breakup. So, the conclusion about that speech is, first point, large force factor is incompatible with low inductance and low moving mass. You can choose the kind of motor structure you want with vintage magnet, with neodymium magnet, with that kind of magnet. You can do what you want. It's the root cause is the physical link between the force factor, the inductance, and the weight due to the design of the motor structure. In the same way, you can use the cone you want, exotic material, beryllium, what you want, is your cone is not attached on a voice coil which strictly follows the movement of the signal, it's useless. The stiffness of the suspension, as I said, we would like to keep it linear, and the damping, I just mentioned it just before. So we need to cut the link between the force factor, the inductance, the resistance, and the weight of the voice coil. We need a constant FS to preserve the dynamic in low frequency. And we need a large frequency range with a very smooth breakup to avoid shrips sounding. A solution I want to introduce today is named VKI for Cartesian Innovation. It summarizes all the innovation we developed during the last decades. And so I'm going to explain why we believe this can help to push away all the limits we know until now for the loudspeaker design. First, the motor structure of the VKI is based on SiC radial magnets. It's important to say SiC radial magnet because we already have some speakers on the market with very thin radial magnets. Because in the industry, to put radial magnet, they charge the magnet first, and next they put it in the motor structure. With thin radial magnet, you can do it. With large radial magnet, you cannot do it because the magnetic field is too strong. So what we did is we developed our own magnet charger able to charge radial magnet. And this is game-changing because we can use SiC radial magnets. We put it not charged in the motor structure and we charge it in one time at the end. Because it's a large radial magnet, we avoid the magnetic short circuit on the top and the bottom of the magnet. So we have the full height of the magnet usable. So you see on that graph the radial magnet and you see the voice coil moving in red and what is the consequences on the force factor. If you want a linear force factor higher than 12-15 millimeter, no need to change the voice coil. We just change the height of the magnets. So no need to change the weight of the moving part, no need to change the inductance. We just change the height of the magnets. The second point is about the suspension. 10 years ago, we developed a spider technology named dynamic spider. The idea is to keep the stiffness of the spider constant until the maximum excursion, and so we preserve the resonance frequency unchanged on the full nominal working of the drivers. We use this dynamic spider technology on every single driver we produce. Even the cheapest speaker sold by Cartesian used this kind of spider. We have our own tool to make our spiders. And next, we change the resin and the material according to the resonance frequency you expect. Last point is about the cone. So we have two technology for the cone. We have we name it hexacone. It's a paper cone embossed with hexacone structure on the back. It's very light, it's rigid, but it's not damped. We have another one, it's a CGF. It's a composite material, it's very rigid, it's well damped, but it's heavy. In that driver, we use these two technologies together, and the ideas I put it from the beginning to explain. You see the profile of the cone, it's convex and concave. It's not only convex as usually. And we have a CGF dust cap, very large dust cap in the center, which make the link at the junction of both profile, convex and concave. In that way, we create a shield, very rigid and damped. So the cone breakup of that speaker is very smooth and very easy to manage. Next one. So this is the result of that driver. So in that example, this one. It's WOM 185 VKI. We can adapt the driver according to your needs. It's just one real concrete example to put something on the market and make it real. And so, as you can see, the force factor is nearly perfectly linear until more or less 10 millimeter. The spider is also very linear. On the subwoofer, it's even more linear, and we have an inductance nearly constant at 0.15 millihenry. So it's very unique on the market to reach in the same time large force factor with nearly 12 Newton per ampere value and high excursion and 0.15 millihenry inductance. Usually you need a big voice coil to do it, and you have 0.4 millihenry or something like that. This is the distortion of the driver. So the most important, in fact, with distortion is not the value is to see it's linear. There is no peak in the useful frequency band. And the most important, I believe, is how the THD increase when you increase the sound pressure. Usually, when you increase the sound pressure, you see some peak appearing somewhere because there is some failing inside the speaker design. With that technology, we avoid that. The last curve, the red one, is 105 decibel at 1 meter. And we still have 1% distortion from 200 Hertz to, let's say, nearly 2K. This is the frequency response. It's done in IEC baffle, anechoic chambers, and the frequency response below 100 Hertz is simulated in a vented enclosure tuned at 35 Hertz, if I remember correctly. What is important to notice with that is, first, we have a sensitivity higher than 90 decibel for 2.8 volts. So for a driver of that diameter, it's 185 millimeter. It's pretty good. We enlarge the active surface area because the surround is very special, and the glue landing for the surround is only a line, so we don't lose 1 inch on the speaker diameter only for surround landing. The directivity is nearly perfect up to 2 kilohertz, so you can build a two-way system with that. And the cone breakup at the end is only by 3 to 4 decibel, which is very easy to manage with a second-order passive filter. You do the job and you don't hear the cone breakup sounding. The enclosure is a vented enclosure. It's 25 or 30 liters, and the tuning frequency is maybe 35 Hertz, something like that. Last point to notice is the impedance curve. So we are nearly 100 ohm on the FS, so it means high QMS. And we see the linearity of the inductance at the end of the band. It's not the usual impedance curve we have with high excursion capability drivers. This is just to show the transient response capability of the drivers. What is interesting on the left is to see there is no lagging on the useful band. So it's clean, I think. And also the step response show how fast is the driver. This is quickly the second example. It's the brother of the first one. It's a subwoofer version, so we change the surround, we change the voice coil, we change the spiders. We just change a little bit the demodulation rings inside the motor structure. And we see the excursion capabilities up to more or less 15 millimeters. We say 15 millimeters because we stop at 80% of nominal value, but we can continue with 50% if you want, up to more or less 20 millimeters. So for that speaker, diameter is pretty unique. You see also the linearity of the spiders. You see the THD, which is lower in low frequency because it's dedicated to very low frequency extension. And we have an inductance value, which is 0.4, 0.35 millihenry, which is not so high, and it's quite stable over the full dynamic over the full excursion of the drivers. On our website, you can adapt the driver up to you. So this is the first step for those who want to test it. If you want something very special, you just send us an email with your technical brief. We can sign an NDA if you want. We are used to do it. But on our website, it's a very convenient solution. You can choose if you want a Cooper ring, if you want which kind of voice coil you want, titanium former, polyimide former. If you want a softer spider, you want to change the FS, you want carbon fiber dust cap instead of CGF and so on. You do the speaker you want. You just select the option. And we explain each part at each step of the assembly. Well, that's it. If someone has some question, just feel free. Thank you.